I'd like to welcome everyone to the fifth episode in the Spectrum Scale User Group Expert Talks. Today's talk is an update on functional enhancements in Spectrum Scale. This is a kind of core system talk today. So this is one of a series of events we've been running this year as a replacement for our in-person events. We're up to number 5. We've got another couple planned for the rest of this year as well. So if you don't know about the Spectrum Scale User Group, we are an independent group. We do work very closely with our colleagues at IBM to develop the events. We have a very active email mailing list and a Slack community. I encourage you to look at the Spectrum Scale User Group website. We post all of the slides from our talks on there afterwards, and we're also posting the replay videos from the digital events as well. So just a little bit about who run the user group. So I'm Simon Thompson. I'm based in the UK. I'm the chair of the user group in the sort of UK and European region. Also helping to coordinate the user group worldwide, we have Christy, Bob and Bill, who are based in the US, and Chris, who's based in Australia. So most of us are all IBM champions, so we're recognised for the community input that we put in. So on the user group website, you can see the list of the previous talks in there. Today's is the update on Inode Management, vCPU scaling and NUMA considerations. And then the next 2 talks we've got lined up in a couple of weeks. We have Spectrum Scale CSI interface, so that's using things like Kubernetes and OpenShift with Spectrum Scale. And then we have best practices for information ILM policy management. We're also looking at how we arrange a bunch of events around SC20. So normally we'd have an in-person user group at SC20. We're looking at how we might work that for the SC20 period. If you've got any thoughts about how we should run that type of event, please let me know. Send me an email. My contact details are on the user group website. We have to make a decision on what we're going to do with that in the next sort of week or so. So if you do have thoughts, please do let me know. Also, if you're interested in being a customer speaker at SC20 event, then please let us know as well. So we have 2 speakers today. Neither of them have spoken at a user group event before, so I'd like to thank them for agreeing to speak with us today. We have Karthik, and Karthik is a senior software engineer in the Spectrum Scale core team. He's got 18 years experience in design and development of distributed system software. He specializes in file system core and database management, and he also told me that he specializes in troubleshooting Spectrum Scale corruption related issues. So hopefully that bit of his job isn't too busy. We also have Mike Harris as well. So Mike's also a senior software engineer in the Spectrum Scale core team. His background is in operating system kernel, device drivers, virtualization, and system software. And he focuses on NUMA concurrency, high CPU count concurrency. And he's worked on the NUMA scaling as well as the DMAPI interfaces in Spectrum Scale. So with that, I'll hand over to the first of the speakers today, which is Karthik, and thank him for agreeing to speak today. I should mention as well, we have a Q&A session running, so you can ask Q&A within WebEx events. There should be a panel there. When you ask a question on there, I can interrupt the speakers and we can ask the questions of the speakers. We might sort of wait till they finish their slide before I interrupt them. But I'll pass over to the first speaker now. Thanks.
As Simon mentioned, I'm a senior developer in Spectrum Scale. So today the theme of my talk is Inode Management in Spectrum Scale. So I'll talk about various data structures associated with inodes and the mechanism of Inode Management in the file system. I'll also touch upon some related enhancements in this area, and hopefully you'll find it interesting. So let's dive right in. Right. So we'll start with one of the most important data structures in Spectrum Scale file system, and that's the Inode file. So this is the one data structure that you don't want damaged, otherwise your file system becomes pretty much useless. So this Inode file is basically a system file, and you can think of it as a huge array of Inode records. Each of these array entries are indexed by what we call the Inode number. A lot of our Spectrum Scale utilities have direct access to this array, and they depend on being able to traverse this array to do their job. For example, restripe. You can also, as an end user, access this traversal. So you could write a policy script that will do some operations on a set of inodes, and behind the scenes it actually traverses this array and looks up each inode to see if it matches with your policy rule. Another thing you can do with this array is you might know the inode number of a file, but you might want to find the path of the file, so you can use tools like tsfindinode to do the mapping for you. And basically tsfindinode would walk the directory structure, directory tree, and then look for matching inode numbers and print that. So we have two ways of traversing the file system. One is through the inode array, the other is through the directory tree, and we use each of them depending on what we are looking for. So this is basically what the inode file looks like. On the right, you have blocks like any other file, any other user file, except these blocks are of metadata block size, something you can configure when you create a file system. You can have a different block size for metadata and data. So you have one block containing many inode records. Inode records default to size of 4 kilobytes. So you can fit as many inode records of 4K depending on the metadata block size. And you have all of these various metadata blocks that make up the entire array. And this inode file, there is one for the active file system to track all the inodes in that active file system, and then you have one each for the various snapshots that you may have in the file system. One thing about the way snapshots work is that whenever you try to modify a block, be it a data block or a metadata block, the old version of the block is preserved in the snapshot before the block is modified. And this is the same with the inode file as well. So if you are updating or changing any attributes in the inode, then the whole block of the inode gets copied into the snapshot before that inode is modified. You might notice that you copy the whole block even if you have just modified one inode in the block. We will see why this is significant in the later slides. The other thing with the inode file is that it can grow in size. You can add more inodes into your file system depending upon your needs, and inodes can be added up to the maximum limit, which is either defined by you as the end user, I mean the file system administrator, or it can be automatically determined by the system. So there is an overarching limit that decides what is the maximum number of files the file system can support. And the heuristic really tries to estimate how many small files you can fit into the file system's data space. So depending on how many disks that you have in your file system, it will try to estimate how many files that translate into, and that would be the upper limit of inodes you can add to the file system. The user specified limit has to be lower than this, otherwise you get an error. Right. So that's some basics on the inode file.
If you make the block size 8K, can you stuff 7.5K in a file into an inode?
So there is a range of block sizes you can specify in Spectrum Scale, and you can find that in our FAQ. So the minimum is 64K block size. You can't go below that, and you cannot change the inode size. The inode size is 4K. So either inodes can contain user data if they are smaller than the 4K, or they would have to move into a separate data block. So you cannot have partial data in the inode and partial outside the inode. So it's either all in or outside.
But I think the important point that Ken was asking was that, can I have an 8K inode size? And you can't, right? Metadata block size is different than the inode. Inode is fixed at 4K, so if the file is smaller than 3.5K, then you can stuff it in there, but you can't do what was being asked on the QNO.
That's right. The inode size is determined at 4K. You can have smaller inode size, 512, and some odd variants of that, but we don't. That's not the normal practice. We go with the default 4K in almost all deployments. So you can't change that. And if you want to increase the inode size as a RFE, you have to imagine that would make your inode file larger, your inode records larger. It increases the I/O overhead for all sorts of inode processing. So you don't want to make the inode size larger just to accommodate small files. So I hope that answers it. Moving on to Inode Spaces. So the whole idea of Inode Spaces was invented to support independent file sets. And to understand why, before independent file sets, we had what we call dependent file sets. And the whole idea of file sets is that we have a logical partitioning of the file system namespace. So each directory tree rooted in a file set is isolated from other file sets. So you cannot have hard links between two file sets. This sort of gives you a kind of isolated view of the file system. It's sort of like a mini file system. That was the basic idea. But it had some problems. For example, even though the partitioning was there for the namespace, behind the scenes, there was really no separation for the inodes. So the inodes were all in the same container, so to speak. So what happens in this case is that if you have to scan one particular file set, right, that is process the inodes of that file set in certain fashion, then there is no way for you to restrict the IOs to only those inodes, because you really don't know which inodes belong to a particular file set without actually reading them. So you end up reading every inode in the file system just to process the inodes belonging to a particular file set. So this kind of scan is expensive. So you get the isolation, but not really the benefits that you might expect from such an isolation. The other thing is with snapshots. You might want to snapshot one particular file set, and the problem with snapshots is that, as I mentioned before, snapshot works on the block level. So if you modify the inode of one file set, then the entire inode block has to be copied into the snapshot, and it's very likely that the other inodes in the block might belong to different file sets. So you are incurring an overhead of snapshotting a file set, same as snapshotting the entire file system, because you are copying inodes that you don't really need to. For these reasons, it was decided that the best way to get these benefits is to actually do this partitioning at the physical level as well. So the implementation is that we have a range of inodes, and we partition that range into smaller sets of inodes, smaller contiguous ranges. And then we mark each of these smaller ranges as belonging to one or other inode space. So the benefit of this is all of the inodes within the inode space, they would be assigned to one independent file set. And there is a very deterministic and simple way to tell where the inodes of your file set, of your independent file set, begin and end within the entire inode file. And this determination is possible because of the simple translation we have between inode numbers and inode spaces. So I'll explain that a bit. It should be interesting. I have shown here a picture of how we use masks to determine from a given inode number a certain portion of the inode number as denoting the inode space and the rest denoting the inode number within that inode space. So it's a sort of a binary level partitioning. And if you see this example here, you can, given the inode number 423178, you can eyeball the above range and determine that it must come under inode space 1. And it's just as easy to determine programmatically, because if you see here, the masks isolate the inode number. The inode number taken out leaves the inode space ID, which translates to 1. This is also interesting to see how we would then grow inode spaces and add new inode spaces, how the block masks and the space masks change. So here's how it's going to work. Let's just say that we started with the inode space 0, and inode space 0 had 8192 blocks in it, right? So that would mean that we would have a block mask with all of these bits. That we start out with the block mask having these bits, meaning that given any inode number, they will all be masked into this inode space. And we'll have a all set of zeros in the inode space mask because we really don't have any inode spaces other than the 0, 1. Now let's say we add inode space 1, which means we introduce one more bit in the inode space mask right after the end of the inode block mask highest bit. So the effect of this is that this particular area, it kind of gets duplicated. So you get another 8192 blocks allocated, and now we call this chunk as inode space 1. Now if we extend the inodes in the inode space 0, we used up all of the inodes over here, that is this number of inodes, so we wanted to add some more. Then how does the expansion happen? Now this time we want to extend the inode block mask. So the inode block mask gets a 1 bit right after the highest bit in the inode space mask, which is right over here. And the effect of this kind of bit addition is that you take this entire inode space 0 and inode space 1 partition and you just duplicate it. So you get another set of inode space 0 and inode space 1 partitions. And as you can see, inode space 1, the second partition is almost empty or fully empty because there is no inodes inode space 1 needs to extend into, which is okay because this is the way we arrange inode spaces, and it's not necessary that we have to actually allocate blocks in this space. This can be a hole in the inode file, and if inode space 1 grows further beyond the 8192 blocks, then it can start to use this section of the inode space, and it gets inode blocks allocated over there. So so that's basic idea of how we use block masks and space masks to partition a single inode file into multiple physical inode spaces, and gives all the benefits that independent file sets bring in. So you get better scanning performance of inodes, and you also get snapshots which dependent file sets don't have. So Inode Allocation Map is the third important data structure, I would say, in the file system. The second being the file set metadata file. So the Inode Allocation Map is basically a system map which, just like the inode file, is a huge array, except this array is made of bits instead of inode records. And the purpose of this allocation map is it gives us a fast way to look up the allocation state of an inode. Is the inode free? Is the inode in use? This greatly optimizes file allocation because you don't have to scan through an expensive large inode file just to find an inode that's free and ready for use. So the bitmap here is a quick indication of what inodes are available for use. So each bit in the bitmap is actually a fat bit, what we call a fat bit, composed of 2 bits. And we need 2 bits for each inode because we have 4 states that we need to track. 2 of them, of course, being free and in use, but then we have 2 others which are transitionary states during inode creation and inode deletion. And we'll talk more about inode allocation deletion, and we'll see how these additional states help with recovery when you have interrupted operations. So just like the Inode file, the Inode Allocation Map file is also supports Inode Spaces. It has to, and it also uses the masks to identify the various inode bits in each inode space, just like the inode file. The same mechanism. One thing with the inode allocation map is that we are going to be referring to this allocation map from different nodes in the cluster when we are allocating files, which means that we need to ensure that there is a good amount of concurrency in this kind of lookup operation. Every lookup operation would need to lock a portion of the inode allocation map, and we want different nodes to be able to lock different portions so that they don't trip on each other and we get maximum parallelism. So the way we achieve this is that we break the inode allocation map logically and also physically into smaller units called segments, and the segments are the unit of locking when we want an inode to look up this inode allocation map. So the number of segments that get created initially, that is a function of your file system creation arguments, specifically the -n argument, which specifies the number of nodes that you estimate this file system to work with, and the number of metadata disks that you're adding to the file system. So it comes up with a number of segments that is expected to maximize the parallelism of locking the inode allocation map. So that's the basic idea here. And we also have a configurable parameter, global configurable parameter, max active ialloc segments, which specifies how many segments each node can lock at the same time. Sometimes it helps to have more than one segment locked by a node, and I'll explain more in the later slides, but we do have that feature here. Just like inode file, we can have holes in the inode allocation map, which can make it sparse. Right. So that was a brief idea of what the map is for, and this will help with the further concepts we'll be going through. Some things that we need to remember with the inode allocation map, specifically as relating to performance. So here are some things, some gotchas that we found over various engagements with our customers. So there is a misunderstanding that the inode limit, the limit that I talked about in the first slide, which the user can specify for the amount of inodes that is allocated for a particular inode space. So this limit that we give as part of the file system creation command, mmcrfs, only applies to what we call as the root file set, the very first independent file set created as part of the file system creation. It is not the limit for the entire file system for all the independent file sets taken together. It's just a portion of it. Misunderstanding this might make you allocate more inodes than absolutely necessary, because you might be thinking you are allocating that many inodes for the entire file system for all the future inode spaces that you will be creating, which is not the case. Also, another best practice is that you don't pre-allocate a large number of inodes during file system creation or at any other time. It's possible to pre-allocate inodes or change the number of inodes currently available using mmcrfs and mmchfs and the corresponding file set commands. The thing is, if you accidentally pre-allocate too many, more than what you need, there is no way to go back. You can't deallocate or undo what you have done. The amount of blocks that are added to inode space stay around for the life of the inode space. You'll have to delete the independent file set of that inode space to actually get rid of all of those blocks. So it's something you don't want to make a mistake with. It's far better to let the inodes grow on demand when there is a pressure in the number of available or free inodes. The system automatically expands the inodes up to the maximum limit in increments. So that's the better way to do it. Also, don't use a very large value for the number of nodes that you estimate the cluster to be, because we use this value to determine how many segments to create, that is to help with parallelism. Now, you might be in a situation where you have created a lot of segments, but you don't have enough inodes to populate these segments with. So you might end up with a lot of entry segments and segments with very few inodes in them. Why is that a problem? Because if you have segments that have less number of inodes in them, they get used up very fast. And once they get used up, the node needs to lock another segment for it to start doing allocations again. And this locking process, as I'll explain in the coming slides, is prone to conflicts. So you don't want to have nodes try to lock segments more often. That is one way to have a performance degradation. So you don't want to use too large a value, but at the same time, you also don't want to use too few values, because if you create too few segments and you have, let's say, double the number of nodes, then the nodes will be competing for locking those segments. So again, you'll have an issue with parallel allocation in different nodes. So it's a balancing act, and people have got it wrong before. And in 504, we provided an undocumented way of reformatting or doing a relayout of the Inode Allocation Map. And this is not a trivial operation, so needs to be done with IBM support help. But it is possible to re-optimize the Inode map if you made a mistake in the various arguments that decide how it's laid out. Right. Any questions at this point?
So there's two questions. So one is about the relaying out the allocation. So do you know how long it takes, and can it be done while the file system is mounted?
Yes. So we can do it when the file system is mounted. So the way it works is it creates a shadow inode map, and it formats a copy with the right layout after due experimentation, and then it populates that inode map with the bit states from the original map. So all of this is happening in a second copy, so it's not interfering with the original copy's usage. Only at the very last moment, there is a quick swap done, and this swap kind of invalidates all the segment caches in all the nodes. So that's the only disruptive operation, but that's a fast operation because we are simply swapping the location of the Inode file pointers. So yeah, it can be done online, but we don't want you to just try it for the fun of it. We'll have to think about it a bit before we go down this path.
So there's another question coming related to that. Are there counters that report the lock collision waiters for lock contention to indicate whether a relayout is desirable?
Yes, if you do find that parallel file allocation is slower than you expected, we can start some diagnostics. We are able to dump the various allocation caches that we have on the nodes, and that tells us what was the collision frequency and where is the real contention here. From the outside, a lot of problems look the same. So we'll have to do diagnostics to figure out what exactly is the root cause for the contention. And if it turns out it's because the layout is bad, we can do a relayout.
So there's a bunch of questions just coming in. I've asked one that somebody asked a few minutes ago, and I'll come back to the other ones. So it's about Inode Spaces. So what determines the number size of the Inode Spaces? Or is that only for independent file sets?
Right, so the Inode space is controlled by the end user or the file system administrator. You can change the maximum inodes in Inode space or the currently allocated number of inodes in them using the mmch file set command. So you have an inode limit option to that, and you can give two values. One is the max inodes that you want in that space, and the other is the amount that you want pre-allocated.
More questions coming in, I'm sorry. Why does a large number of NUM nodes influence Mmdf runtime?
Right, so it shouldn't. So what happens with Mmdf, I'll have a later chart for that, but to quickly give you information on that. So we cache the number of free inodes. I'm hoping that when you say Mmdf, you're talking about the inode part of it and not the block allocation part of it. But we cache the free and used inodes in the Stripe Group Manager, and this caching happens by all of the nodes reporting their current inode usage to the Stripe Group Manager. So the Mmdf output is pretty fast because all it does is report on the cached values. If you had to use an option where there is an option where you can do a full scan of the inodes, the actual inode structures on disk, and figure out from that how many of those inodes are allocated in case you need that kind of statistics. So you can do that as part of mmls file set -i. And if you use that option, that is more expensive because it's actually redoing the accounting of the free and used inodes, and that might take time because that depends really on how big your inode file is and what other workloads are running on the file system. But for Mmdf, I really think it should be fast. If it's not, yeah, we'll need to investigate.
So how does the number of nodes relate to the number of segments?
Right, so we basically want each segment to be available to each node. Sort of one segment per node is the ideal policy, right? So if you have 1,000 nodes, you want at least 1,000 segments per inode space, right? Because we really don't know if all the nodes are going to be working on the same inode space or not. So you want each of these nodes to be not blocked for locks. So they all need to be able to lock one segment for themselves. So that's how it starts out, but it's not simply that we have allocated as many as there are nodes. We actually allocate more. And the reason being that you could have segments that have run out of inodes, free inodes in them. And when we run out of inodes, we start an inode expansion automatically if it's not already done. And there is a trigger threshold for that. And that threshold only kicks in when 75% of the inodes are used up. So that means even if 3/4 of the segments are full, we still need to be able to support all the nodes which might be parallelly locking segments. So the rough rule is that we allocate 4 times the number of segments as there are number of nodes in the file system. but it's not a straightforward algorithm. There's a lot of more calculations going on. But yeah, this is a good indicator of how these two values relate to each other.
Are there general recommendations for initial inode allocation?
Start with the minimum that you need, because you can always extend or grow. You can either grow explicitly or anyway the implicit inode expansion gets kicked in. There used to be a time when inode expansion was slow for various reasons, but it's been improved over time. So you really don't have much of a penalty for on-demand inode expansion. So idea is that you start with the minimum number and then grow as needed.
So there's a number of questions. I'll ask one more and then we'll move on. And if we've got time at the end, we'll come back to some of the other questions.
Sure.
How is the Inode Allocation Map and its segmentation affected if metadata Nsds are added or deleted?
It doesn't. If once you have created the Inode Allocation Map, the layout doesn't change. So that's what you have now. So if you want to move metadata disks around, that's up to you. But all that movement only affects is the blocks, the data blocks, or the metadata blocks if they hold metadata. But the Inode allocation map itself is not dependent on any of these operations. So the only relation is that you need space to store the Inode allocation map somewhere. Other than that, the concept of Inode, tracking the Inode, has nothing to do with Nsds themselves. Yeah, we'll move to the next one. So yeah, we talk a little bit on Inode expansion. I know I talked a few minutes back. So Inode expansion is basically the act of adding blocks to the Inode file or the Inode allocation map file. It's sort of a mirror process. The Inode allocation map is sort of a compressed version of the Inode file. So maybe you don't really have to add that many blocks to the Inode allocation map. But nevertheless, these two maps, these two data structures have to be increased in capacity to accommodate the new number of inodes. This expansion is limited by, as I said before, the maximum inode limit that you as a user can set on that inode space, or by the overarching limit that the file system determines based on how many small files can fit into the file system. So it will refuse to increase the max limit beyond that number. So Inode expansion can be both automatic and manual. I already mentioned that the trigger threshold is if the number of free inodes falls below 25%. And when it does not just expand the inodes up to the max limit, it does it in increments. So it expands by 25% of the amount of allocated inodes. And if that happens to be too much, there is even a cap for that. The idea is that you don't want Inode expansion to be spending a lot of time, because what you're trying to do here is solve an immediate Inode allocation space crunch. And you're only doing what is necessary to make that allocation possible. And you're allocating a few more just for optimization. But you don't want to keep doing this and take a performance hit on the file system. The trigger for the expansion, we used to do this during background sync. That happens like in 30-second intervals. But we changed that so that we check this threshold every time the free space count changes. So that's a more reactive way of expanding inodes. So there used to be a case on very heavy used file systems where you would run out of number of free inodes. The inode space would kick in after some time, but until then, all your inode allocations are blocked or aborted. So in order to react faster, we check more often now. I already mentioned the relationship between the number of segments to the parallelism. So we want it to be 4 times for this reason because of the threshold, which is 25%. The manual expansion is also possible. You can use mmch file set. You can use mmch file set to affect even the root file set. And you can also use the mmch fs as well for the root file set for this expansion. One thing that we enhanced quite some time back, it's not a new change, but for completeness, we moved from version 1 of format of the Inode Allocation Map to version 2. So basically, we just made Inode Expansion faster. The way the Inode Expansion would format the allocation map with the extra space was causing a lot of disruption by invalidating existing caches. So we came up with a better way to do that without invalidating existing workload that were using the various segments. So there is a small or impossible penalty for doing the version 2 way of things. I won't go into the details because we are, it seems, short on time, but the idea is that this really works out faster overall. The next topic is the Inode Manager. So the reason the Inode Manager exists is it's not to coordinate the locking of the various Inode segments, because there is a chance that you might correlate this with the block allocation manager, whose job is to dole out the various block allocation map segments to the nodes. So there is no such thing here. I'll talk about how Inode allocation works later, but the job of the Inode Manager is very simple: to make Mmdf faster and also to determine when it is time to do the Inode expansion. So the way it does it is it keeps an accounting of what the free inode is. It has to start the accounting at some point, and it does that by initializing itself by reading all the segments in the Inode allocation map, counting the bits that are free, and it does this during a stripe group manager appointment. So the first time you mount a file system, or if you use mmch-mgr to move the stripe group manager, this Inode Manager initialization kicks in. There were a couple of problems, performance related, in this area. So for one thing, whenever you do Inode expansion, the free space accounting is again changed in a big way. So we used to force the Inode Manager to do a reinitialization by reading all the segments again, which was, as you can imagine, expensive. So this was blocking the Inode expansion. So we changed the Inode Manager functionality, so it no longer reinitializes itself by reading the segments from disk, but it actually adjusts its free inode value based on how you expanded the inodes. And the tricky part here is that there are nodes in the cluster which might be sending their free inode accounting to the Inode Manager, and that accounting is sort of additive or added on to the existing statistics. So we had to revise the way this accounting is done, so that after we adjusted the Inode Manager for an expansion, we don't mess up the accounting because other nodes sent double accounting of the free inodes. So this is in 503. In 504, what we did was we also improved the initialization of the Inode Manager, not just for the Inode expansion. It's when you start mount a file system for the first time and you need to initialize the Inode Manager. So it used to take a lock on every segment, read that segment, do a accounting of the bits in there, which was very expensive. So we decided to just read the whole Inode map file blockwise and without any locks. As you can imagine, when you don't use locks, you are going to get stale or dirty values. It's possible. And so the accounting might be off when you initialize it this way. But fortunately, when you are initializing the Inode Manager, it means that the stripe group manager is also initializing. And as part of that, there is something called as an async recovery. So some aspects of a new stripe group manager is synchronous. It has to complete before any other task in the file system can continue. Some other aspects can be done in the background asynchronously. And one of those things is deferred deletions. I'll talk more on that later, but that involves reading the Inode Allocation Map. So this deferred deletion is now overloaded that while it is reading the Inode Allocation Map asynchronously, it also corrects the stale accounting of the Inode Manager. So essentially this change lets Inode Manager quickly initialize itself with some roughly correct values, and then the more correct or accuracy is achieved in the background asynchronously after some point. So there is eventual consistency kind of situation here. I'll take a pause here just to see if there are any questions.
I think there's one quick question. Is there a minimum version in which automatic Inode expansion is available?
Inode expansion was always available. There is no minimum version. The only thing is I talked about an enhancement. So 504 and 4.1 pretty much made it fast. 503 and 504 they made it even better. So it's only about the improvements, but not the feature itself. The feature itself is available in all versions. So I'll move on then. Yeah, so far we saw the various data structures. So now we'll look at the three main usage or use, what do you say, the data flows of the Inode. So those are creation, updation, and deletion, right? So you have to start by allocating an Inode when you create a file, and this slide is about how that process works. So to allocate a free Inode, first the node has to pick a segment from which to do the allocation, right? So one obvious candidate is that the segment has to be for the independent file set in which the Inode is being created, right? You can't provision an Inode from a different file set, Inode space. So you have a bunch of segments available to you. You don't have the entire Inode map file segments available. It's just only the set that belongs to this Inode space. That's what you start with. Then the logical place to look is that you already have locked or cached certain segments. You start looking in them first before you start looking outside that. But even among those, like I said, you can have max active ILOC number of segments per node. Which of them do you pick, right? So the idea is you might, or the workload might be creating lots of files in a single directory. And in that case, we want all of those inodes to belong to the same segment, because it's more likely that you might want to delete the whole directory at a later point. And that means you are freeing up the inodes from a single segment, which is much more efficient than trying to free up inodes from multiple segments. So we use the parent inode number, parent directory inode number as a hint for finding a free inode. We look in one of the segments for file allocation. The next time you allocate a file from the same directory inode number, this lookup, it's basically a hashing lookup, will most likely end up on the same active segment. The other aspect is that if you are allocating files for different directories, you would ideally want them to be on different segments. And that is because it's most likely that you might be deleting those directories at a later time from different nodes in the cluster, which means if both those directories share the same inode segment, now they have to contend on the same segment, locking the same segment, which is a bottleneck. So to have more parallelism, we want different directory inodes to go into different segments. So that's the idea behind picking the segment. And the next thing is, of course, if you have identified an inode, you're going to lock the inode, read the inode data structure and all that. So it would be good if you already have those kind of inodes cached in your node. And that is possible because if you track the inodes that have been previously deleted, you could use that list to quickly see if any of those inodes are still available to reuse. So we maintain what is called a DLOC history. It's just a list of deleted inodes per segment. So it's important that we keep this for each segment because there's no point in looking into the DLOC history of another segment and reusing that. We are looking to allocate an inode from this particular selected segment. Finally, if you don't find a free inode in the segment that you have chosen, then it's time to go look elsewhere, right? You have a lot of other segments in the same inode space to pick. Maybe they don't belong to you, they are owned by some other node, but that's okay. You just have to find one which has enough free inodes for your use. But to do this, you are going to invalidate the segment from the other node, read it from disk, and so that is an expensive operation. You just don't want to do it blindly. You want to pick segments that have more chances of having free inodes. And for that reason, every node maintains something called as a hint map. And the hint map is nothing but an estimation of whether a segment has free inodes. Now, if a node already owns a segment, it can look into the segment and see if it has free inodes. So the hint map for such locked segments will have a definite answer of does it have free inodes or does it have no free inodes. But once it loses the lock, the segment can be used by any other node, and the free and in-use states of the inodes might change. So it downgrades its estimation to probably has inodes or probably no inodes. And it downgrades based on the previous value that it had before it lost the lock. So previously, if it thought that there were definitely free inodes, it now becomes, it probably has free inodes. The reason this is important is you want to look first into segments that you know for sure has free inodes, and if no such segments are found, then you look as the next candidate into something that probably has free inodes, and so on. Some enhancements here, again, the 5 version, is that you could be doing file allocations in parallel, multi-threaded, and each of them could be using the same algorithm for inode allocation. And if they coordinate on what they found, they might not have to do repeated searches. So this was one enhancement we did. The other is that we had not accounted for empty ILOC segments earlier, because we would generally populate the file system in such a way or create the file system that the Inode allocation map was well or healthy looking. But as I said, there are people who format it in a suboptimal way accidentally. And so you might have a lot of free or empty segments which really don't have any inodes in them. And there is no point in actually locking such segments and searching through them. So we made some enhancements in that area. So moving on, once we find there are no segments which have free inodes, we don't give up yet, because there is a thing called Inode Expansion, right? So we trigger an Inode Expansion if it is already not running. As I said, Inode Expansion would start on a certain threshold, but it's possible that that expansion is a little delayed because it only checks it whenever the free inode count is updated in the Inode Manager, and it's possible that nodes have not yet updated the Inode Manager on the free inodes. So if it's not yet started, we start one Inode expansion process, and then we wait for it to complete. If it completes, it means we now have more free inodes. If it doesn't, then we give up. We have no way of allocating a file now. And that could happen because you already used up all of the inodes up to the maximum limit in that inode space. So this is the sort of workflow. By the time we find the inode, we have a few more things to do at this point. So we start by marking the inode as being created in the Inode Allocation Map. Of course, we have to mark it, otherwise someone else will try to use it, right? So we have to start by marking it. Then we initialize the inode on disk and create the directory entry. And then once these two operations are completed, we can then move the transitionary inode allocation state in the bitmap from being created to in use. So this whole transitionary state is for the case where you have node failure in the middle of all of this. Now all of these operations are protected by the GPFS journals, so you do have recovery bringing things back as before, but in some cases recovery would just simply drop that particular inode and directory creation, and we would be left with a bit that is in being created state. And then it is up to the async recovery, which I mentioned before, would be scanning the Inode allocation map to clean it up. So when it finds something like with being created, it will clean up that bit state so that inode becomes available for use again. So this is a short of what really happens with inode allocation. I'll move on because I bet I'm running out of time. The next thing is, once you're allocated, you want to update the inode. The problem with inode update is every time you change the size of file or you modify some metadata related to a file, or even let's say you just modify a data block of a file, the end time of the file would change. And all of these parallel operations which are protected and work very well in Spectrum scale still need to update a single data structure for the whole file, which is the inode, right? The 4K data structure can become a bottleneck for parallel block level operations. So we can't have each node ping-ponging on the inode locks, that is taking the ownership of updating the inode, which is very inefficient. So we choose to create a coordinator as an authority who will make all the changes to the inode, and that is called the meta node. So meta node is simply a role for every file that is being used in the file system, and it is responsible for making any updates to the inode or indirect block or basically any metadata related to that file. And it will take the responsibility of flushing the changes to disk and protecting it through recovery logs and all that. The other nodes, all they do is they cache various inode fields, indirect block fields for their intermediate use, but when they have to really make a change to the inode, they send a message to the meta node to make the change on their behalf. So this way, the meta node can collate a lot of changes and save on the I/O as well. And because each node just has to do a network send instead of doing an I/O, taking a lock and doing an I/O, it's also quite efficient. So this meta node is elected dynamically, so it's not a pre-configured setup. Any node that starts to operate on a file the first time, that node becomes the meta node for that file, and that meta node role can move to another node depending on what kind of operations are being done on the file. Maybe some other node is doing a operation like chmod, which requires exclusive lock on the inode. So in such case, the meta node moves to that node. And also, if there is a meta node designated, but there is no operations being done on the meta node itself, it's just another node that's doing all the changes to the file, it makes more sense for the meta node to be located as close to that node as possible. So then we move the meta node over. Meta node, unlike other node roles like file system manager, token manager, meta node can move into remote nodes, that is nodes which have remotely mounted the file system. Meta node additionally also helps with something called as fine-grained directory locking. Basically, if you know, directories are huge blobs of blocks, and each directory block contains a lot of entries. And it is possible that different nodes are operating on different entries of a directory, and they are not really trying to operate on all the directory entries inside a particular block, right? So if we were to use the traditional way of locking a whole block, that becomes again a contention. So we want a more granular way of locking directory entries. And so we have this meta node as the coordinator for that as well. And all of these other nodes, they update directory entries via the meta node. And the meta node consolidates and writes the block in one shot. So there is no ping-ponging of the block across different nodes. So meta node is pretty useful, and it's also very relevant to the next topic, which is inode deletion. I'll take
two questions. Okay. Is there a way of identifying the meta node for a file?
Yes. So you can dump the FS Manager. I think that's the dump section, and you should be able to see if if you dump all the open files in a node, mmfs adm dump, and I believe it is open files, but I'll get back to you on that. But that section has the list of currently open files, and also tells you which node is the meta node for that particular open file.
And the second question was, if a node goes down and the meta node is unable to get updates from those nodes, how are updates maintained by the meta node?
Right. So it's part of committing any change. You have to first commit it into the logs, right? So if a node has committed into its logs before it went down, and before it sent its updates to the meta node, it is recoverable. A node does not give back a response to the application that it has finished the operation of, say, the file creation, without making sure that operation is recoverable. So either that data is there with the meta node logs or the originator node, but in either case, we guarantee that if we have committed file creation, it is recoverable. Was that all?
I think there's one more question came in, that can we limit meta node to migrate to remote node? Also, will it help in improving performance if we limit meta node in storage cluster? I think it's a bad idea to try to limit the meta nodes to storage cluster. Imagine you have a 1,000-node cluster and everybody is writing to their own file. Having them be the meta node for their own file means you have 1,000 meta nodes and there is no need to coordinate anything with anybody else. If you had only, like, say, a few Nsd servers that were acting as the storage cluster, and you were trying to use those and restrict the meta node to just those, now all of a sudden every client node has to go and talk to these few meta nodes, and all the RPC overhead will now go over the network for all of this, right? So you don't want to do that, right? The scalability of Spectrum scale depends on this kind of a distributed nature for certain actions like this.
We do actually, on our biggest clusters, we do prevent the meta node from jumping around. It's not a bottleneck in limiting it to the storage cluster itself. There's a number of jitter reasons. I'll defer to Karthik, but that is a best practice on our current largest clusters. Yeah,
but that is a really, really large cluster.
Yep.
And you have enough nodes there that we don't think, right, that's going to be a limiting factor.
The key is you wouldn't want it with just one or two storage nodes, but with a very large cluster and enough storage nodes, it's actually preferable.
Yeah, so that's a good point, right, John? So I think if you had like one or two ESSs, right, where you wind up with like only like 2 or 4 SSD servers in your storage cluster, and you still have 1,000 nodes, right? Maybe not the best practice there, but yeah, I guess if you want to go for the extreme scale, right, trying to limit it to storage cluster and having, because if you have dozens and dozens of storage nodes, right, then you have enough capacity to be able to do that.
Thanks, PC. Thanks, John. I think the one interpretation of the question is whether we can move the meta node into a remote node explicitly. Today, you don't have an option of controlling where the meta node lives. It's the file system that makes the decision. And the thing is, yeah, it moves to a remote node if the remote node is doing more operations on the file than the home cluster. But it is also the case that there could be many remote clusters accessing the home cluster. And in that case, we can't keep sending the meta node to each of these clusters in turn, because moving across clusters is more expensive. So in that case, we have the algorithm where we firmly place the meta node in the home cluster, even if all the activity is being done on the remote clusters. So the idea that I'm trying to convey here is it's very tricky to determine where the meta node should be placed. So it's best left to the file system to make the determination. So inode deletion, just like allocation, we have set of steps that we have to follow because you have updates to different metadata to achieve the effect, and we need to ensure that all of this works fine. First is when you unlink a file or delete a file from a directory, it's possible that the file is hard linked, so you have multiple link counts to that file. So just deleting one of them is not enough to get rid of the underlying single inode. So until the link count goes to 0, we just update the inode and do nothing else. But if the link count goes to 0, then it's time to get rid of the inode because there is no reference to that inode in any of the directories. We start by marking the inode state in the Inode Allocation Map as to be deleted. So this is again a transitionary state, and it is more relevant than the being created state because the being created state is very short-lived. You almost always get to the in-use state right after being created because that's how short the whole set of operations is. But in the case of deleting an inode, there is a POSIX requirement that deleted files can still be open. So applications can still have open file handles to that deleted file. So you may not have any linkage to that file, but you still have in-memory access to the file. And I think this is the basis for a lot of tricky temporary file creations where you just create a file, unlink it, but you still have open file pointer and you have a exclusive safe access to that file since nobody else can open it again. The thing is, until the last open file instance goes away, you can't do the inode deletion. The inode still has to be around. So how do we accomplish that? So before we go there, this to be deleted is there to protect the inode cleanup in case the node goes down right after you set the flag. So you set the to be deleted state, and now the node goes down, which means you probably lost all the references, in-memory references to the file, or not, depending on if other nodes have references to that same file still. But whatever the case, there has to be some kind of a cleanup now required once the recovery is started, because in case there are no more references to the file anywhere in the cluster, then we have to clean up the inode. Otherwise, there is an inode that is not visible in the namespace, but it's available taking space and not reachable. So we need to do that cleanup, and the basis for doing the cleanup is we don't want to scan every inode in the file system to look for such inodes which have 0 link counts and not deleted yet. Rather, we look into the Inode Allocation Map and we check for this to be deleted bit state, and if it is set, we know this inode needs some processing. We don't directly go and delete the inode right then because we still have to check, does this inode still have memory references in some other nodes in the cluster? And once we determine there are no more references, only then we move to the next step. um, we call such inodes that are that have 0 links but not yet deleted as inodes that require deferred deletion. And you can find out how many such inodes exist in the file system. And this may be significant because as an end user, you might use some directory traversal mechanism to determine how much space is used in your file system. And then you might discover that the amount of space available is less than what you come out from this calculation. And that's because there are these inodes that are yet to be deleted, even though you can't access them from the directory tree. So if you use the mmfsadm dump deferred deletions command, you can get an estimate of how many such inodes exist. All it does is look in the Inode Allocation Map for to be deleted bits and just adds them up and reports it to you. We made multiple enhancements in 5 versions for deferred deletion. So one thing was deferred deletion was not interruptible, which means sometimes it would hold up other activities that depend on this. So we now made that interruptible, and also we made it multi-threaded. Earlier, deferred deletion was a single thread operation. As you can imagine, if you delete a lot of files in a very short period of time, they all get bunched up, queued into this deletion state, and you want them to be processed as fast as possible. So what happens when you're trying to mark a inode as to be deleted? The difference from the inode allocation is that when you're allocating an inode, you're free to choose any segment which has a free inode to pick that allocation. But when you're deleting, you don't have a choice. You just have to delete that given particular inode. And it is possible that particular inode resides in a segment which is currently being owned by a different node. So earlier we would take a lock on the segment, the other node would invalidate its cache, and then we would do the to be deleted marking, and then maybe the other node gets it back again. But you can imagine that if you had a lot of files to delete, all in very different segments, you are now locking and invalidating so many segments in the cluster, and that can be a big disruption. So what we have added is sort of dealloc shipping, where we send this bit flip state to the node that actually owns the segment and not do a revoke. Okay, this was the setting of the transitionary state, but we still have to wait for all of the references to go away. And what we do is we set a flag on the open file object that tells us, remember to delete this inode when this reference goes away, right? So the node that finally gets rid of all its active references to that file, and it sees that this destroy on last close flag is set, now has the task of actually getting rid of the inode. But it can't be sure that no one else in other nodes in the cluster are still referring to the inode. So what it has to do is it sends a request to the other nodes to relinquish their metanode token. Now what I glossed over in the earlier slide was that whenever you first become a metanode, you get a certain node token, metanode token, which is a stronger version of it. But other nodes also get a version of the token which is weaker, and they need it before they do any operation on a file. So basically, the metanode token is a sort of indicator of how many nodes have active references to a file, right? So when this node requests other nodes to give up their metanode token, they'll only do that if they no longer have any references to that inode. And this way, we can determine if it's a prime time to delete the inode, right? But what if there are nodes that still have references? Then this node cannot be waiting forever for them to get rid of the references. This node just returns and does nothing it's now the responsibility of those other nodes which have references to do the cleanup. So whichever node closes all its references to such an inode, it tries this whole step again to see if no one else is holding references, and then progresses with the cleanup. The cleanup is pretty simple. You have to read the inode, all its blocks, free up the blocks, mark the inode as deleted, right, and commit all of this to disk. But this can be expensive operation if the file is very large, right? So we don't do this cleanup synchronous to whatever unlink operation triggered it. Rather, we do it in the background. So we queue this deletion into a big queue that is serviced by a lot of threads. And that is why you might see confirmation of file being deleted, and there are no other references to the file. You confirm that no one else is looking into this file, but you still don't see the space being reclaimed. That's because the background deletion is still probably working through its list of queued up inodes and hasn't got to this particular inode yet. The background queue is present on each node. So maybe some node is overstressed. You did a lot of deletes on that node, so its background queue is big. And even though it's multi-threaded, it always helps if you distribute the deletion so that every node has a certain chunk of inodes to work with. But it's not really that big of a problem, because one aspect of this deletion is that you have to free up the blocks, the data blocks allocated to the inode. And that means you have to mark the allocation state of the data block in the block allocation map file, which is another system file I haven't talked about. But basically, it has the same restrictions. Another node might be holding the segment of that block allocation map file, and we don't want to revoke it just for the deletion case. So as part of the background deletion, we also queue such the block free up requests to specific nodes that own the respective segments. So because this is asynchronous, we can afford to do all of these back and forth network operations. But in the end, the result is that while you may not see your application stutter when it's deleting files, if you are low on either the inode limit or the block space, then you might find that even though you have deleted a lot of files, you have not reclaimed the space yet. So in those cases, you just have to wait for it. Or in case there is a node failure, then you get into this deferred deletion mode, and then it gets even slower because now you have to scan the whole inode map and then repeat this or redo this deletion. Yeah, once you successfully deleted it, or not just queued it to the background deletion thread, but actually got rid of the inode, then it is time to mark the inode as free in the Inode Allocation Map. And that again follows the same mechanism as marking the to be deleted state. So it's a bit of a play around, because in cluster systems, maintaining cache coherence is the most difficult problem, right? And naturally, with such things like allocation and deletions, there are a lot of data structures that have updates. So keeping them all correct is the real challenge. So basically, that's an idea of the workflow of an inode and the various different operations we have been doing. I think I mentioned some enhancements, but that's not the end of the story. There's always scope for improving things. So we look forward to hearing from you on any enhancement requests, and we'll try to accommodate them. So that's pretty much what I had. And do we have questions?
So there was a question, which I'll have a quick look at the question. Sometimes when we delete large amounts of data, it takes a significant time to show free space in df-h. Do you need to run an restripe fs or something to reclaim the deleted space faster?
No. So the restripe command has applies to restoring the replicas, inconsistencies, or ensuring whatever level of replication that you have in your blocks is satisfied. It can even rebalance blocks across disk so there is more balanced usage, but it certainly does not help with reclaiming a space from deleted files. So as I said, the file deletion is queued up as a background thread. If we were honest and did this synchronously, then you would actually notice this delay in your application because your rm command would not return until the whole file has been deleted. So what you see really is that the background thread is taking its time to clear up the space. There is a reasonable expectation, like maybe wait for a few minutes or a few hours depending on your file system throughput or how many files you deleted in the last few minutes. So you can always get an estimation of how many files are in that to be deleted state by using the dump command I mentioned earlier. So if you have an idea of how fast I/O happens on your file system, you can put a rough upper limit on how long it will take to recover all of these inodes. But if you still don't see the space being reclaimed after this point, or if you don't see the deferred deletion count reducing over time, then it's a reason to investigate and figure out the problem.